Alright, well, making a video for you guys. Let's see here. We'll see how far I get. I have a lot of examples to share with you, and a little bit of theory, so let me just get straight into the theory. I'm not sure it's even really theory, more of just calculational tools. We talked about Rule 1 last time, and so what I'm about to show you, these are just nice tricks to calculate residue in like a nice simple fashion. So if f of z has a simple pole at z naught, then we can calculate the residue just simply by multiplying the function by z minus z naught and taking the limit as z goes to z naught. That gives us the residue. Remember, the residue is the coefficient of the reciprocal term in the Laurent series about the isolated singular point. If it's got a double pole, then we take the limit as z goes to z naught of the derivative of this. Now, you never... it's not usually like, I mean, this looks kind of scary, like, oh, it's got a product rule and stuff, but like in practice, what this means is that you're just looking at the, if f of z has a double pole, that means basically you can write it as the quotient of like phi of z divided by z minus z naught squared. So you're really just differentiating the ratio of f by that. Well, is that the right way to say it? Well, I'm going to go on here. There's a great temptation to start this video over again and again. I must resist. Now this one is not in my notes, but it's useful. If you have an order m pole, then you can calculate its residue by looking at the limit as z goes to z naught of the m minus 1th derivative divided by m minus 1 factorial of this thing right here. And I'll actually prove that for you. And then of course we have rule 3, which says that if you have f and g holomorphic at a point, and if g has a simple 0 at z naught, then the residue is simply the value of f at the point at the z naught divided by the derivative at z naught. And then if we take the case f equals to 1, that gives us rule 4. If g of z has a simple 0, then residue of 1 over g z naught is just 1 over the derivative of g at z naught. So let's look at the proof of this one here, because that'll help elaborate the point I was just making. So here's the proof down here, because that's essentially one of our singularity theorems before, right? It said if z naught has a pole of order m, then there exists a holomorphic function phi such that f of z is phi of z divided by z minus z naught to the power m. And really, that rule ends up just looking at the derivative of this phi. And that limit is really just decoration, truth be told. Anyway, so if this is true, then multiplying by z minus z naught gives us this equation I'll call star. And then, on the other hand, we know that it's an isolated singularity, so there's a Laurent decomposition. So we can write f of z as the sum. And I really could put, since we know it's a pole of order m, I really should just put m there, right? So let me just fix that. Change my infinity to a minus m. There we go, all better. And then, by definition, the residue is the minus 1 coefficient of the Laurent series centered at the point, right? And by algebra, on star right here, basically just multiply the z minus z naught to the m into that. That gives you this formula. Phi of z is equal to the sum k equals minus m to infinity of a sub k z minus z naught to the k plus m power. And so we're interested in the residue. That's what we're trying to calculate here. And the residue comes from when the power here, let's call it n, is equal to m minus 1, right? When we have k equals minus 1, that's what we're interested in. All right, but on the flip side, phi is a holomorphic function, right? Which means it's analytic at z naught, and that means that there's a Taylor expansion of it, right? Phi of z is equal to the sum, the nth derivative of phi at z naught divided by n factorial. And so if we match up coefficients in the case that the power n is equal to m minus 1, well, lo and behold, we get a sub minus 1 is simply the m minus 1th derivative of the phi evaluated at z naught divided by m minus 1 factorial. That's the formula for the residue. And that's almost, honestly, like, when I think about this rule, I really think about this. This is more often than not what I would actually use when I implemented this rule. Maybe I'll try to make up an example here in just a second. But, so that maybe it would almost be better to write these rules in terms of the phi, each one of them, okay? But anyway, and then if you take the limit, and so basically this implies that the residue is the limit as z goes to z naught of the m minus 1th derivative of z minus z naught to the m over m minus 1 factorial times f of z. And that is really nothing more than the fact that I've differentiated phi, and phi is equal to that. Well, phi is equal to right up here, right? So it's just, yeah. So let's see here. Before I get to my newfangled example, let me show you some old examples that I have. And so this is from an old problem 91 from yesteryear. So there are so many solved homework problems on my website if you look. So if you need more examples, goodness gracious, there's so many there. The likelihood that my bank of examples overlaps with your homework is, I would say, very high. I'm probably solving one of your future homeworks right now, or possibly one of the homeworks you've already done. My apologies. Wait, no, I apologize for nothing. Let's see here. So residue of 1 over z squared plus 4 at 2i. So if you multiply this by, well, this factors into z minus z plus 2i times z minus 2i. So basically, let me just scribble on here a bit. The way to think about that, right? One way you could think about that is that 1 over z squared plus 4, it's equal to phi of z divided by z minus 2i, at least for the purposes of z naught equals to 2i, right? Where the phi of z is equal to 1 over z plus 2i. So if we look at that general rule I just derived, this is the m equals 0 case of it. So there's no differentiation, there's just evaluation of the phi of z at z naught, which in this case gives us 1 over 4i. In other words, actually the mth rule, it gets you rule 1, rule 2. Like, if we think about it logically, hopefully logically, how else do you want to think? Do you want to think illogically? I mean, I don't. Why think at all? Anyway, so this, well, yeah, rule 1 and rule 2. Rule 1 is really the m equals, goodness, this is the m equals 1 case, this is the m equals 2, this is m. Notice when m equals 1, there's no derivative, and the, then the 1 minus 1 is 0, well, 0 factorial is 1, so, m equals 1 is that, m equals 2 is that. So if you understand the rule for the order m pole, it automatically gives you rule 1 and rule 2. Okay, so we'll come back and prove rule 3 in a minute, but I wanted to do some examples first. All right, so there's that. This one, z, well, 1 over z minus 5, z to the 5th minus 1. Let me zoom in a bit here. All right, well, that's, I say 1 over 5. So what am I doing here? Oh, this is rule 4. So what we got is, I have g of z for rule 4. G of z is equal to z to the 5th minus 1. Of course, g of 1 is what? 0. And what's g prime of 1? Well, that's 5 times 1 to the 4th, right? which is not equal to 0. So if we have g of 1 is 0, but g prime of 1 is not equal to 0, that makes it a simple 0. And so by rule 4, we can just 1 over the derivative of the denominator function evaluated at the z0 gives me the residue. There's that. And let's see here. Here we've got z over log z at 1. And so here the f of z is z, and log of z is g of z. The derivative of g of z is 1 over z. And so if we evaluate 1, we get 1 over 1 over 1, which is 1. So there you go, residue of that. And you're like, wait, let me just see. You were saying that log z didn't have isolated singularities. True, log z has singularities. It has a whole branch of singularities, right? The branch cut, the negative real axis. But as long as we're not there, log z is holomorphic, so it plays nice with all this stuff, right? Then this next example, and these are problems I think are from Gamelin actually. Residue of e to the z over z to the fifth. So I think I just did this by direct calculation. So this is I didn't use the rules. I just used direct Maclaurin series. Like e to the z is that. So if you look at it, the 1 over z term comes from this. So that makes this the 1 over the coefficient of the 1 over z by multiplication of series is just 1 over 4 factorial. But of course, you could also, now that we have the mth rule, we could do it that way, right? So this is really what? This is a pole of what? So that's essentially f of z equal to phi of z divided by z to the power 5, right? Certainly the exponential is holomorphic at 0, and it's non-zero too. So this is, anyway, this is clearly a pole of order 5, which means that the residue of f at 0 is, according to our newfangled rule here, we're supposed to do the fourth derivative of, remember this is, like I said, in practice, this is how we actually apply it, right? In practice, we actually apply it like that. So the residue, so I take the, let's see here, the fourth derivative of e to the z, which is, well, e to the z. That's the fourth derivative of e to the z, and I have to divide by 4 factorial. Okay, great. And then I'm supposed to take that and evaluate all of that at z equals to 0. So what's that give you? Well, not surprisingly, we get 1 over 4 factorial, which of course is 1 over 24. So no surprise here. This way is the beauty of the the rule for order m pole is it properly applied. It can save you the hassle of doing like the Maclaurin calculation. Now, I like to be able to do both. I sometimes forget this rule, right? But if I don't, it's pretty nice. It saves me the trouble of working out the mechanics of the Laurent series directly. Of course, working out the mechanics of the Laurent series directly is always an option. Okay, so there's that. Now, why are we interested in all this? I will get back to the proof of Rule 3 here in a minute, but of course the reason we're interested in all this ultimately is what? Integration. So let's look at just a couple easy examples, which my old problem 92 while we're at it. Sorry, it's a little bit messy, but here we are. So maybe I'll add a picture. So here we have the integral of sine z over z squared, right? So if you want to think about that, basically you got this circle of radius 1, right? And there is simply z equals to 0 is the only singularity in that circle, right? And I had to counterclockwise. So here's your modulus of z equals to 1. Then the residue theorem says that the integral of f over the unit circle is equal to 2 pi I times the sum of the residues of the singularities that are inside the unit circle. This is what Cauchy's residue theorem says. And so there's only one, the double pole at 0, right? And so we can calculate the residue of sine z over z squared at z equal to 0, and we can get that it is 1. Now how do I do that? Well, the derivative of sine is cosine, and so we do cosine evaluated 0, that gives us 1. So basically I'm just using the double pole. See, the double pole, see, I almost, you have to think about what that looks like. What is z minus z naught squared in this context here, right? So like the double pole, the residue theorem here, it just looks like this. Residue of, let me get in frame here. All right. The residue, oh, too busy. The residue of sine of z over z squared at 0 is equal to the derivative of sine, which is, you know, I'll write it out here, d dz of sine z, right? And you could say, well, divided by 2 minus 1 factorial, right? Divided by 1 factorial, it's kind of dumb. And then you evaluate that as equal to 0. Well, that's just, let me cut through the static here. That's just cosine of 0, which is 1, right? So come down here, yeah? And that's why that integral we can just calculate just like that. It's 2 pi I times 1, which gives us 2 pi I. All right? Let's look at the next example. And these might well be homework problems of yours, but I don't mind doing them because I think it's, you know, I'll do it, then you do it again, and we just all need to understand at the end of the day. Okay, so let's see here if I can get it in frame like I like. So here we have the integral around the, you know, I'll draw another circle here. I'll do my work in blue this time. So we've got a circle of radius 2 in this problem, right? And the circle of radius 2, right, modulus of z equals to 2. We want to think about that in the counterclockwise sense. And you got a pair of singularities in there, see, because z squared minus 1, right? It's 0 at both minus 1 and 1. Those are your singularities. So in this case, Cauchy's residue theorem gives us 2 pi I times residue at 1 and plus 2 pi I times residue at minus 1. And it just so happens that the residue at 1 and minus 1 can be, you can get them by rule 3, which is the derivative, the function on the top divided by the derivative of the function on the bottom evaluated at the point. So the function on the top is e to the z, the derivative of the denominator is 2z. So we have e to the 1 over 2, and over here, when we plug in minus 1, we get e to the minus 1 over 2 times minus 1, which is minus 2, like that. And so, lo and behold, we've got a 1/2 e and a minus 1/2 e to the minus 1. Well, that's exactly the hyperbolic sign. That's sinh of 1, because we've got a common 2 pi I, and so there you go. It's really, really nice how easy it is to calculate these. When you think about the mechanics of what is involved here, if you were to directly parameterize these curves and run through the integration at the level of like real calculus, it's oh man, it's really nice what we're doing. I mean, if you were to descend into real notation and actually work out the mechanics of the real and the imaginary part of that previous problem, like what is it that you're calculating there? It's pretty cool. It would be a mess. You know, it's exponentials and sines and cosines, and they're being divided by, you know, a quadratic. That's not particularly nice. It's a little bit nice, I guess. All right, next example here. Z to the fourth over sine z. Now this one's interesting because we have to think about where is sine of z 0? Well, we know sine of z is 0 at multiples of where? Pi, right? So this one here, I guess I should do a purple circle. Yeah, here we go. Whee. All right. And, sorry, I'm easily amused. What can I tell you? So here, this is the unit circle. And again, we're assuming it's counterclockwise oriented, so like these. And where is the denominator of the integrand 0? Well, it is 0 at 0, right? And also out here somewhere at pi, and over here at minus pi, and so forth and so on forever and ever. Now notice that 0 is a simple 0 of the denominator, because derivative of sine is cosine, and cosine of 0 is 1, so that proves that the 0 of sine at 0 is a simple 0. And as such, we can use one of our handy-dandy rules to calculate the, whoa, yowzers. Oh, I gotta be careful though, because z to the fourth is also 0 at 0, which makes this more complicated. Yeah, so this doesn't quite fit this doesn't quite fit the pattern. How to say this? Well, yeah. I'm trying to think, guys, if this fits one of our rules or not. I mean, this calculation is fine. It's good. You know, this is a good way to do it. Maybe I should just not... I'm trying to fit everything into the rules at the moment, you know? And that's just kind of silly. Like, the rules are tools. Use them when you can see how to use them. If you can't see how to use them and you prefer to do the Laurent calculation directly, then by all means do it, as I've done here, right? So let's see here. Z to the fourth over sine z, there's the Maclaurin expansion for sine, but I've already divided out 1 power of z. And then what in the... wait, what? What's this? Oh, I factored out a z cubed, I guess. What? Sorry, guys. I'm a little bit mystified by what the meaning of this right here is. I think this calculation here is okay, but why does it help me? I suppose this helps me because this shows that... What does this show? This right here, since the denominator is holomorphic at 0, right, with value 1, so you've got a function which is holomorphic with value 1 at 0 in the denominator, and my numerator is z cubed. Well, this expression right here shows you that we're actually looking at something which has a 0 of order 3 at 0, actually. So it turns out that z equals to 0 is not a singularity in the genuine sense. It's actually a removable singularity. And the residue of a removable singularity is 0. So there you go. All right. Yeah, that's all I want to say about that. All right, so let me go back to the proof of rule 3. I will get past these rules here pretty soon, guys. We're going to look at some interesting integrals in today's video. Interesting as defined by me, of course. Ha ha ha. Where is, so like rule 1 was on page 148 of the notes. We looked at the proof of that last class. Here's rule 2. We looked at the proof of that last class. Let me see here. I gotta get things in order, otherwise we're gonna have trouble. All right, there we go. I even got an old test to look at here before too long. Here's rule 3. Let me get my cover sheet. So I think it's pretty much the same thing we've already gone through proof-wise, but let's just sort through it. So here's rule 3. And I do think you should be able to prove the rules, because really the proof of each one of these essentially boils down to, like, you've got an isolated singularity, so you've got a Laurent decomposition, and then the proof is really mostly a calculation. So these are good proofs in the sense that the proof is exactly the same kind of calculation that we're doing in the problems we're working. Anyway, so here we go. Rule 3. F and G holomorphic at Z naught. G has a simple 0 at Z naught. In that case, the residue of the quotient of F and G at Z naught is simply F of Z naught divided by G prime of Z naught. So the proof has cases. So first of all, the case that's considered is if F of Z has a 0 of order n greater than or equal to 1, which would be the sort of situation we were just up against in the last example I just did, right? It's exactly that example. So, ooh, I think rule 3 would have done it for us, wouldn't it? We could have just... I was trying to stop talking about the rules, you know, for that example, but it sucked me back in. What can I tell you? If I can find it again. So, look, rule 3. F of Z equals Z to the 4th. F of Z equals Z to the 4th. G of Z is sine Z. Sine Z has a simple 0. So rule 3 says you do F of 0 divided by G prime of 0, which is 0 divided by 1, which is 0. So we can derive this by rule 3 if we just open our eyes. All right. And, okay, so moving on here. So suppose F has a simple 0, rather a 0 of order n, larger than either a simple or double or triple, whatever, a 0. If that's the case, then we can write F of Z as Z minus Z naught to the n times H of Z, where H of Z is non-zero at 0, right? And G of Z, of course, is Z minus 0 times K of Z, where both H of Z naught and K of Z naught are not equal to 0 by construction. But then the quotient of F and G is given by this, which is Z minus Z naught to the n minus 1 power, quotient of H and K. And if you plug in Z naught into this for n greater than or equal to 1, you just have either, let's see here, you either have, in the case n equals to 1, you have H of Z naught divided by K of Z naught, which is a number which shows you that it was a removable singularity, or you have 0. And so, yeah, I guess in both cases it's a removable singularity. It's just sometimes the removable singularity is the quotient of H naught and Z naught, and otherwise the removable singularity, the value, actually is 0 itself. Anyway, in either case we have residue 0, and so it comports well with the formula up here. F of Z naught is 0. All right. All right, so then what? Well, if next, suppose that F of Z naught is not equal to 0. If that's the case, then we can use rule 1, because then you've got you got a simple pull, right? If you have F of Z divided by G of Z, F of Z naught's not equal to 0, and G of Z has a simple 0, then you're looking at a simple pole, which means we're back to rule 1. And by rule 1, we have this, which is that. Oh, that's kind of cool. So look at that. In my heart, I have a suspicion there's a way to do this with just like straight calculation of Laurent series, but this is kind of a cute argument, so we'll bear it. So the quotient of f of z and g of z in this case is z minus z naught. Well, excuse me, by rule 1, it's the limit of z minus z naught times that, but then if you like, you can rewrite that as division in the denominator. I mean, why not? Because if you do, then you got a derivative. Yay! And there it is. That's rule 3. So, yep. So there's that. All right. And so that's all I have to say about the rules for now. Let us move on here. So I'm going to stick with my notes for just a bit. And once we're past the notes, then I've got a bunch of examples to show you. So I'm going to try to go somewhat fast through the notes here because, because I can, I suppose. Let's see here. So integrals featuring rational functions. So if we consider, so let me just, I have the picture down a bit here, but I'll draw it again. These circles are too small. I'll just have to freehand it. So you got, basically what's going on here is you got a half circle. Oops, well, I tried. You got a half circle and a diameter. And so the half circle is going from, minus r here to r here, and it's going, see, we want it to go counterclockwise, so it goes like this, and then half of a circle, let's call it, I call it c sub r, right? So half of a circle, I'm denoting it cr in this discussion. So d is, where's d? Well, d is the interior of that red curve, okay, so it's like in here, right? This is D. Man, I wish I had some colored pencils on hand. Nah, I'll content myself with markers. There we go. And so Cauchy's residue theorem says that the integral around the boundary of D, right? It's equal to what the what? Me no like. So I'm saying in here you've got these points where f is singular, say z1, z2, z3. I guess with my usual picture, singular, singular, singular. All right, so there's apparently k of these singularities just for kicks. All right, and Cauchy's residue theorem says that the integral is that. Well, this isn't true. The integral, look at that. That is, that's no bueno. That should be boundary of D. That's what Cauchy's residue theorem says. That's not CR. Dummy wrote these notes. Idiot. Idiot. I blame the editor. All right, let's see here. All right, there we go. Sorry about that. I guess it's just as well that we're going through these notes together today. So in particular, well, look, now that's a mystery. Where'd that come from? Well, it came from the fact that the boundary of D has two pieces. The boundary of D, see, D is this region. And the boundary of D either is the diameter at the bottom or the half circle, all right? So that plus that is equal to 2 pi I times the sum of the residues. Now, this is something we can calculate with our rules. And these are, well, these are two integrals that are interesting. And what is actually interesting is that oftentimes we can make an argument that this piece goes to 0 and the limit as r goes to infinity. But let's just say this much. If we have a function, so this is just a general setup, I said at the top of the page rational functions, but there's nothing assuming rational function yet, right? As long as you have a function that has isolated singularities in the upper half plane, I mean, it can have isolated singularities elsewhere, but in the upper half plane, you need all the residues in the upper half plane, and you can write down Cauchy's residue theorem here, assuming R is sufficiently large that you're capturing all the singularities, right? Okay. And yeah. So let's talk about the case of a rational function. For a rational function, suppose, come on. Here we go. So if we think about a rational function where the degree of the denominator is at least 2 more than the degree of the numerator, and if we say basically n minus m is greater than or equal to 2, and we assume that we also want to assume that there's no real zeros. A real zero of the denominator will be a fly in our ointment that we can't pick out just yet. We'll get there. There's something called fractional residue that takes care of that later, but not today, okay? So no singular points fall on the minus r to r. And then in the homework that I know you guys did, we showed that you can bound the denominator in a sense that you can find in r. Well, let me get through it. Basically, the point was we argued that we can, let me just get it down to here. And I'll try to do this stuff again in class because it bears repeating. But anyway, so basically here's the deal. The modulus of f of z is, of course, the modulus of the ratio of the denominator to the numerator to the denominator of polynomials defined in the rational function. And so if the p of z has got coefficients b0 through bm, well, then by triangle inequality in the numerator we have that. But by the homework problem, we can make q of z. I mean, in our homework we showed that there's an m that we can make. Let me just write the stupid result down again. We proved that for r sufficiently large, we could make the modulus of q of z. What was it? Greater than or equal to m times r to the n, if I remember right. No, not the same m. Let me call it m tilde. Right. We proved that the for r sufficiently large, we could make the modulus of the polynomial bigger than that. And so that's nice because then you're making the denominator smaller for that m tilde, which makes the fraction larger. So we can use that estimate to do this kind of thing. Basically, I mean, I'm just saying sort of schematically, think of the absolute value of a sub n over 2 as my m tilde. We proved you could do that. And anyway, so if you look at all this, let's see here. I divide the top and the bottom by r to the m, and that gives me just the sum of the modulus of the coefficients, or possibly them divided by r to a power. But like basically you've got bm, modulus of bm, da da da, modulus of b naught divided by r to the m, dividing the top and bottom by r to the m. And so, of course, if r is greater than 1, then you can just do like, as many terms as there is here times. Well, anyway, you can use like the maximum of the. You could take the maximum of the absolute value of these coefficients and replace it. Anyway. Let me work this out in class. It's probably better if I do it there. bottom line is we can bound the rational function by m over r to the n minus m. And again, I think I'll spend a few minutes of class on this because it bears repeating, and you know, I'd like to think everybody's watching the video, but well, yeah, you never know. But I hope you're watching. Although if you're hearing this, I guess you're watching. Anyway, so moving on here, we can bound the integrand for a rational function on the the circle of radius r, and so then if that's the case, well, then we can use the ML theorem, right? And so we've got m times 2 pi r divided by r to the m minus n, but this is 2m pi over r to the n minus m minus 1, but remember we assumed that n minus m was greater than or equal to 2, so this power is at least r, and so in the limit, right, in the limit r goes to infinity of this, we have that, which goes to 0. So the integral over the outer loop over the half full circle is just 0, which is really cool. And so that leads us to this right here, which is that the integral from minus r to r of a rational function, come on, stupid paper sticking. The integral from minus r to r of a rational function is equal to 2 pi I times the residue, because the other piece, the integral over the half circle, goes to 0 in the case that the denominator has at least 2 more degrees than the numerator. And so I should give this thing a name. Let's call this the residue formula. Residue formula for rational function integral. I need to give it some kind of name, because there are times when I am perfectly content to let you use this as a theorem, and there are other times where I really want you to go through the arguments that I just went through as they pertain to a specific example. All right. Let's look at some examples here. So here is a nice example. Really, I mean, it is perhaps the nicest example, maybe, for this stuff. I don't know. It is a good example, though. All right, so I want to calculate the limit as r goes to infinity of minus r to r integral of dx over x squared plus 1. I mean, pause for a second here. We can do that integral without complex, because the integral of x squared plus 1 over x squared plus 1 is this inverse tangent. So we know the answer is pi, okay? Because pi over 2 minus pi over 2 is pi. And that's how the inverse tangent works. Now, but anyway, let's work it out here. So the residue formula for rational function integral theorem, I should come up with a easier title for that thing. Rational integral theorem, I don't know. I'll let you guys come up with a name for it. Anyway, using the theorem that I've been talking about the past 5 minutes, if we look at this right here, right? So for f of z equal 1 over z squared plus 1, right? For that function, it has singularities at where? At plus and minus I, because when we factor it, and it's always factoring, isn't it? We factor z squared plus 1. This factors into z plus I times z minus I, right? And of course, only the plus I is in the upper half plane, and it is encircled by every one of these contours for r greater than 1, right? And we're looking at the limit as r goes to infinity, so certainly that I is in there. And so Cauchy's residue theorem gives us 2 pi I residue of that, but we can use rule 4 to calculate that. It's just derivative of the denominator is 2z, and you plug in z equal to I, which is the singularity we're interested in, and you get 2 pi I over 2I. The 2i's cancel, and you're left with pi. And there it is. And to be fussy, this isn't quite the integral of minus infinity to infinity of that, right? This is technically what's called the principal value. When you take the limit as minus r and r both go to infinity symmetrically, that's called the principal value, which I define systematically in section 10.6. Okay, so we'll get there. Okay, and there, yeah, I got a footnote. I've footnoted it. There it is, about the principal value and the difference and blah, 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 whatever. All right, so another example in my notes is this one. Here we're up against the integral of, come on, the paper's sticking. All right. Integral of 1 over z to the 4th plus 1. So the singularities of this are the 4th roots of minus 1, which are those guys. And it's, you know, if we look at that, it's fun to look at the picture of that down here. If I can, yeah, I guess I gotta zoom out. If you can still see the writing or not. Well, probably. So here's the contour we're working with, this half circle. You know, the boundary of the half disk. We're letting the radius go to infinity. And so you see, of the 4th roots of minus 1, this one here, that one there, are both inside the contour. However, the other two of them, they matter not, because they're outside and they do not contribute to the integral over the half circle. And then of course here again we can make the bounding argument, because the denominator has degree 4, the numerator has degree 1, so certainly we can use the ML theorem to make the integral over the half circle vanish in the limit. And so we're just going to have the principal value of this integral, which it turns out is equal to the integral in this case, because it exists. Minus infinity to infinity dx over x to the 4th plus 1 is equal to, well, it turns out pi over root 2. Why? Because 2 pi I times the residue at that 4th root of minus 1, and 2 pi I times the residue of this at I e to the I pi over 4. Let's see here. So these are, it's simple zeros all around. So we can just we can use rule 4 actually. And because how do I know it's a simple zero? Because if I differentiate, first of all, if I plug that in, I get 0. But if I differentiate, I get a 4z cubed. And if I plug that in, I don't get 0, which there it is. It's a simple 0 in the denominator. If you evaluate at the point, you get 0, but you differentiate at the point, you don't get 0 when you evaluate at the point after the derivative. It's a simple 0. Okay, so using rule 4 on both of these, actually, I differentiate the denominator 4z cubed, and I plug in my singularity, and when I do that, I get 2 pi I over 4 e to the I 3 pi I over 4 by the you know, the usual exponential laws for the complex exponential. In this case, I guess imaginary exponential, I should say. Likewise here, notice I got an I cubed in that case. Sorry, I know it's way too small. Let me zoom in a bit. What if you guys are trying to watch this on a phone? That'd be crazy. Oh, even your sad little notepads aren't really adequate. Anyway, beautiful, huge screens, and you guys are all little, tiny little. Anyway, your eyes work. What am I talking about? Okay, so pi over 2e to the 3 pi I, so that's common to both of these. And it leaves me with an I on the first one, is that right? How did I get an I? Where did that I come from? Oh, the 2 pi I, duh. And then the 2 pi I is there, and I cubed. Okay, so that's really, So let's see here. Huh, how did I get the minus? I guess I cubed is minus I, so I over minus I is minus 1, so this is I minus 1. I minus 1, but then I factor the minus out, so I get minus pi times 1 minus I, and then, oh, sneaky move, that is the square root of 2 times e to the minus pi I for, let me draw a picture. What's going on there? What's going on there? 1 minus I. 1 minus I is right here. That, my friends, is pi over 4 down. So as you can see, 1 minus I is equal to the square root of 2 times e to the minus pi I over 4, which is what I did right about here. And then, of course, you've got wait a minute. What the? Wait, what? Oh, that gives me an e to the pi I in the denominator. When I simplify it, e to the pi I is minus 1. That cancels that minus 1 and leaves me pi over root 2, because root 2 over 2 is 1 over root 2. Nice. To quote my son Benjamin, real nice. Anyway, so we can do these kind of integrals. Now, Wolfram alpha gives you the antiderivative in this case of this bad boy is this right here. Nice. Although admittedly, geometric series would give a series integral for this with reckless abandon. It wouldn't be hard. This integral is actually not that bad as they go. Now, the same method we could use to do integrals of like p to the x over q to the x times the cosine, provided that q of x has like a large enough degree that we can still do the ML trick to get this integral goes to 0 on the half circle. That's not quite right actually, because cosine along the imaginary axis is actually cosh, and that's unbounded, so that's not going to work. You can't just do it directly you can't just plug z in here and hope that that's the integral you need to look at. That doesn't work. So what you do instead is you look at p of z over q of z times e to the IAZ. Now e to the IAZ, that guy is bounded, of course. Well, that's not true either. But anyway, let me show you. Let me not try to talk about what happens in general. Let's just look at the example that follows here, yeah? So this one here, e to the, if I can get it in screen, e to the IAZ, I'll zoom out a bit here, e to the IAZ over z squared plus 1. Okay, so we got simple poles at plus or minus I, and so we can calculate the residue of this thing, and it's e to the minus a over 2I. And so the if we think about the again this picture again, we're going from minus r to r, like so. We've got our half circle up here, CR. We're anticipating that the integral of the function in question here is 0 over the half circle because of some kind of bounding argument. Let's see how that goes. So Cauchy's residue theorem, though, nevertheless says that the integral over the diameter plus the half circle is equal to the residue times 2 pi I, which here works out to pi e to the minus a. And so here's the bound for a modulus of f of z. So this example is good. This example shows you what I would mean by calculate the integral without using the bounding theorem, let's call it. All right. Of course, the bounding theorem wouldn't apply to this anyway because it's not a rational function, right? It was the function. The theorem I mentioned about 20 minutes ago was for a rational function, so this is not that. So we really do need to give direct arguments here anyway, and here we do. So the modulus of f of z is the modulus of this, which is straight up equal to, oof, is that true? But z is complex. Dude, I don't believe that. Just because there's an I there doesn't make it real. I mean, AZ has to be real for this to be true. Oh man. Huh. Is there something else here I'm not appreciating? Yowzers. A is real, right? Is A real? I didn't say. That's not good. Well. I am concerned. See, because z equals to x plus iy, right? And if we have e to the, let's assume a is real for the sake of me not going nuts. E to the iaz would be e to the I a times x plus iy. Okay, and that would be e to the iAx, and then e to the I times I is minus 1, so minus ay using, okay. So if, let us suppose then, to rescue this example, we need that a is greater than 0. We're going to assume that. Okay, it's real, it's greater than 0. In that case, so when I take the modulus of e to the iaz, it's actually going to be equal to e to the minus ay. I hope I'm in frame right now. Yeah, I'm in frame. Woohoo! So that puts a e to the minus ay right there. Right? And what is the biggest, what's the biggest that can be? This is stupid. This is funny. This is still true, even though it was, I mean, it's still true, but why is it true? Because y equal to 0 makes that as big as it can be. So the largest that this ever is on the diameter down there. And of course, the half circle does hit the diameter here and here. So at those 2 points, the exponential is 1, and that's the biggest it can be. It drops down to, up here, it's at like e to the minus ar, which is much smaller in principle. Okay, so this is still a reasonable estimate. It's just I didn't reason it. Let's finish this thing. So we get this bound, and then of course as r goes to infinity, that goes to 0 when you look at the ML theorem. Therefore that's all 0, and put it all together, we have the limit as r goes to infinity of e to the iax, yax, because z equals to x here, right? On this right here, we've got z equals to x, and so putting it in, doing the integral on the diameter gives us this, which then looking at the real parts matching gives us cosine over x squared plus 1 equals to pi e to the minus a, and the sine integral apparently is 0 because there's no imaginary part over here. So it's a twofer. By doing this one complex integral, we get two real integrals.